when looking at the different ways in which cyberspace and physical space interact, especially in the context of security, we usually talk about cyber-physical attacks. So we usually talk about cyber attacks that have an impact in physical space. But it is also interesting to look at the other direction. So the direction that goes from the physical space and affects cyber assets. So has an adverse adverse impact in cyberspace. So a physical cyber attack is an attack that is performed in physical space, or at least its entry point is in physical space, but affects adversely cyberspace. So what does that practically mean? Well, there are different types of categories of physical cyber attacks that one can talk about, but I've chosen one for each type of key cyber impact. So one for availability, one for integrity, and one for confidentiality. In terms of availability, the obvious one is that physical damage in physical space or damage in physical space can obviously affect availability. If one cuts a cable, there is no connection, for example, through that cable. Then there is physical manipulation of the sensory input that can breach integrity. That's because when a system relies to a large extent on the integrity of the sensing values, the values that come from the sensor to the controller, from the controller to the actuator, now, then there is also the possibility of affecting the physical environment around the sensor. So that would mean that the system that relies on this sensor input would get wrong data, not because they are in any way manipulated in cyberspace, but because the environment is in such a way manipulated so as to affect the integrity of the operations of the system. We'll talk about this in detail shortly. And the third one is when confidentiality is breached by exploiting compromising emanations. So these are three completely different types of physical cyber attacks, but together they cover the whole spectrum from availability to integrity and confidentiality in cyberspace. So in terms of direct physical damage, the obvious example, as I mentioned, is that some kind of cable is damaged. So the example on the left is from 2011, and that's an elderly woman. She was 75 at the time, who was scavenging for copper in Georgia. Georgia, the country, not the United States, not the states in the US. So while scavenging for copper, she accidentally damaged the fiber optic cable. Now that fiber optic cable had been exposed because of landslides, because of heavy rain in that area, and that single cable being cut, that caused most of neighboring Armenia to lose internet connectivity for 5 hours. That's because Armenia doesn't get its internet connectivity from underwater cables, but it does from neighboring Georgia mainly. So 90% comes from Georgia. And as a result, by cutting this fiber optic cable, I'm talking about a single cable now, the whole of Armenia, or 90% of Armenia, if not the whole of Armenia, lost internet connectivity for up to 5 hours. When she was asked about it, she said that she doesn't know what the web is, what the internet is. So that was an interesting case. She did go to jail, but it's interesting that she didn't even know why. In a sense, she went to jail because she didn't know what the internet is, and she certainly couldn't have believed that, or couldn't have expected that there could have been such an impact in a whole country. And the example on the right is about a train in 2001 in Baltimore who derailed and caught fire in a Baltimore tunnel in 2001, and that led to the destruction of the fiber optic cables and widespread loss of network connectivity for 2 days. Now, obviously, when one lays down fiber optic cables, there is a level of redundancy, so there would be more than needed, of course. However, the tunnels tend to be very convenient places to place such cables. General networking equipment, they are very convenient because they're already there, the tunnels, so there is space for them to put them. There's no need for doing much digging. So it is common to put those cables there, but the problem is that if there is the redundancy, what helps with is that if there is a lot of if there is a need for different cables to be used at the same time, then there will be different cables. But if they are physically in the same space, the redundancy that is achieved in cyberspace doesn't make any difference in physical space, because if there is a fire, then they will all burn at the same time. So there is no such thing as physical redundancy if they're all placed next to each other. Although in cyberspace there is redundancy, of course, if there are multiple cables. In general, physical damage to cables has always been very important. From the First World War, for example, when undersea cables were the first that would be targeted at the beginning of the war, so as to impede communications, especially communications between the United States and Europe. But even today, there are several incidents of very large-scale disruptions of internet, especially in the Middle East, also in Pakistan, in India, in those places mainly, because this disruption is often caused by damage. So it is caused by damage to a number of different underwater cables. There are around 200 or a bit more than 200 underwater fiber optic cables at the moment in the world. These are the ones that carry around perhaps 95%, if not more, 95% of the global internet traffic. And one of the very important ones is this one there. So the CME, so the Southeast Asia, Middle East, Western Europe 4 undersea cable. This is often damaged. Most often the damage is for natural reasons. For example, friction against rocks. Generally, natural. It's a harsh environment, the ocean, so it's expected that physical damage will occur from time to time. But sometimes there have been cases where there is strong suspicion that there was foul play in the damage caused to an undersea cable. Now, considering how important they are, that they carry over 95% of the global internet traffic, one can expect that physical damage is an attractive aim for terrorist acts, for military purposes, for whatever purposes. A lot less straightforward, at least in comparison to cutting a cable, is electromagnetic damage. Now, electromagnetic damage is about the electromagnetic pulse effect, mainly, the EMP, which is a burst of electromagnetic radiation. So this was first observed in the 1960s, if I remember correctly, in high-altitude nuclear explosions, where it was it was observed that one of the effects of this nuclear explosion at high altitude is the generation of electromagnetic radiation that was damaging civilian equipment, and not only civilian, but mainly civilian equipment in a massive geographic area around the explosion. By massive, I mean perhaps the whole of or half of the Pacific Ocean, or perhaps the whole of the United States. So this kind of massive geographical area can be affected by what could be considered as not very strong high altitude nuclear explosion. What an EMP does, and of course a nuclear explosion is not necessary by any means. This is how this was first observed. So an EMP can be created in many different ways nowadays. So an EMP effect can be particularly effective against commercial off-the-shelf electronic devices, and that's because such devices tend to rely on tiny circuits, and these tiny circuits would effectively melt in such if exposed to an EMP. And the military-grade devices, though, would probably be more hardened against electromagnetic interference, and as a result would probably not be affected much by EMP. But it's important to note that EMP does not by any means affect human beings. The human body will not be affected in any way. And also optical fibers are not affected in any way because they are naturally resilient for the very simple reason that they are optical. So they are based on light, which means that electromagnetic interference of any type doesn't really do much. In fact, before I go there, one example I forgot to mention is that a similar effect to EMP can be seen naturally, and this is the result of what we call a solar flare. A solar flare has indeed caused massive disruptions especially in Canada. I remember it was I think the late 80s? I think so. I think it was late 80s, or perhaps early 90s, late 80s, something like that, when a solar flare did indeed cause significant disruption by damaging electronic devices in Canada. To integrity. So rather than targeting availability, we will see now how integrity in cyberspace can be affected by physical space or in physical space. So the examples that I have chosen here, they could be considered as what we call sensory channel attacks. So it is not the traffic that is sent from the sensor. It is not the data that would be sent from the sensor to the controller. There is no form of malware on the controller. There is no cyberspace manipulation of the data. So it is not the data from the sensors that would be affected here. In the sensory channel attack, it is the actual environment around the sensor that is affected. So basically what the sensor measures. So the sensor works normally, and the sensor does operate normally. It does measure things as it is meant to, but it is the environment that is confusing, in a sense, to the sensor. So if we start with infrared, well, infrared sensors, what they do is that they detect objects, for example, human bodies in darkness, by seeing if they are warmer than their environment. And I mean, technically speaking, they monitor the infrared radiation that is naturally emitted of a body, of an object. Now, the weakness of infrared, though, is that this kind of radiation, the infrared radiation, doesn't go through glass. So unlike visible light that goes through glass, of course, because we can see things through glass, infrared doesn't go through glass so easily. So only a fraction of the human body's infrared radiation would go through glass. And what does that really mean? Well, it means that if one wants to confuse an infrared sensor and not be visible to the infrared sensor, to the infrared, let's say, thermal camera, then it would be to an extent sufficient to place window glass, standard window glass, in front of them or between the camera and themselves, and that would make them almost invisible to the camera. Now, of course, to be accurate, no security system is based on something as simple as that. So normally there will be some kind of, if it is, let's say, a motion sensor, it would check the difference in the environment. So it would not simply check the environment, but the difference in the environment. And when one would would place the glass between the sensor and the body, or between the sensor and something else, then the fact that there is a difference there would be sufficient to trigger an alarm. But nevertheless, either way, the weakness is there in the infrared sensing area that glass can, to some extent, defeat it. Now, of course, note that infrared cameras themselves have glass, but it's different kind of glass. It's a glass made of germanium, and germanium is a kind of glass that does allow infrared radiation to go through. So it is transparent to infrared. That's why there are cameras. Otherwise, it wouldn't be possible to have such cameras. Then we can have microphones that are defeated by noise, obviously. So a white noise generator would defeat a microphone, would make it difficult to tell what is heard if there is noise. Ultrasonic motion sensors, these are the types of sensors that you might expect on a vehicle, like a robotic vehicle perhaps, and these are there to detect obstacles. Now, this can be bypassed, first of all, in a very simple way, by moving very slowly, obviously, but very, very slowly. But another way is by wearing a costume made of anechoic material. Now, anechoic means that it absorbs sound waves. So a costume, something that one would wear with, let's say, based on foam or some other kind of anechoic material that absorbs waves, would make it difficult for the ultrasonic sensor to work. That's because the ultrasonic sensor works by sending a beam, an ultrasonic beam, and then waiting for the reflection to come back, measuring the time it took for the reflection to come back, and based on the time it infers the distance. So it can tell whether there is an object in front of it by sending this beam and then this ultrasonic wave, and then receiving the reflected wave. Now, if the material on which if the material that this system is made of is anechoic, then it will absorb some of these waves, and that will make it difficult for the motion sensor to tell how far, for the ultrasonic sensor to tell how far it is from this obstacle. So this is another way of defeating a sensor, in a sense. And then there is LiDAR or LiDAR, LiDAR in American English, LiDAR in British English, which is the equivalent of radar but based on laser. This works by what it does is that it maps the environment around it by sending laser beams, by transmitting laser beams, and again capturing what is reflected back. So in this way, it can get a very accurate mapping of its environment, and that's why it is often used in high-value autonomous systems like driverless vehicles. So these are very expensive usually pieces of equipment, if you compare at least with the other types of sensor I mentioned before. And if one would use it, for example, for an autonomous vehicle, for a driverless car, then this means that the driverless car would depend on it, of course, in order to detect any kinds of obstacles around it, and its environment generally around it, so as to navigate. And it would not be able to do it properly if there are other laser beams that are sent against it. So if there is any laser beam that is pointed against it, then LiDAR will be overwhelmed by the number of laser beams and will be confused. It will not know which one is the reflection of the original laser beam that it sent. So this confusion has been shown in a very interesting paper by Jonathan Petit in 2015, if I remember correctly, or maybe 2016. And it showed that it's possible to, in this way, to neutralize or almost stop or force a driverless vehicle to stop by affecting in a physical way the sensor input to its LiDAR system, to its LiDAR sensors. It is known in general that laser-based systems, laser-based detectors or sensors are affected by reflections. They're affected by mirrors. In fact, Al-Qaeda, some time ago, they had they had shared between them a list of 22 different tips for avoiding drone attacks by the United States. And one of the recommendations that they had in there, in this list of 22, was to place things like mirrors on top of cars, so as to confuse, presumably at least, the laser designators used by the drones for the missile strikes. So it is so generally affecting laser is not unknown that it can happen by having such effect on the reflections. And the third type, after availability, after integrity, the third type of impact in cyberspace based on physical space, based on an attack in physical space, would be targeting confidentiality. Now, for this one, I have chosen the area of compromising emanations. These are sometimes referred to as MSEC, out from emission security or after emanation security, other times as Tempest. Now, these are not exactly the same, but they're similar. So Tempest, which is the code name of the corresponding NSA program, or side channel attacks, that's because information is accessed through a channel other than the intended one. These are not entirely the same, all three, but they're similar in terms of logic. So compromising emanations, this is because any kind of computing system, when it processes information, it produces emanations, it produces heat, it produces sound, it produces electrical signals through the power cables, it produces electromagnetic radiation. And all of these normally is noise. So for most people, this is interference. So all of these, the sound is noise, for example, that is created. When someone is typing something on a keyboard, well, for the rest of the people in the same room, for example, this is noise. But for crafty attackers, this is not just noise, this is a source of information. So this is what can be a compromising emanation. The sound that is created by typing something, this keystroke sound, this is useful information for someone who is trying to breach the confidentiality in cyberspace. It started mainly in the Second World War. One of the first certainly types of electromagnetic attacks, electromagnetic emission security attacks, was when a Bell 131B2 encryption device that was used in the Second World War, I think by the Americans, it would cause spikes on an oscilloscope at a distance. So these spikes would relate to the actual characters that were input in this encryption device. So it was possible to reveal the text that was being encrypted in this device simply by, even in a distance, by looking at this electromagnetic radiation that it was causing and measuring it in the equivalent in the device for this, which is an oscilloscope. In the 1980s, extremely interesting attacks were what we later called Van Eck attacks, after Van Eck, the person who published the first related paper. And this was about stray signals that were emanating from the standard CRT televisions, and he showed that they correlated massively to the video signals showing what was actually displayed on the TV. So, using a directional antenna and an amplifier, it was possible. What he did was to pick up and replicate the actual image from the TV. So he could not see the TV. He did not know what was shown on the TV. He was capturing only the stray signals that were emanating from this TV, and using an antenna, and then he was replicating the actual signal, the actual image, the actual video that was shown on the TV. This was so important that a lot later, 20 years later, when it was shown that the Van Eck type of attack can be done against what the Dutch government was using back then for voting equipment. So it was a system, it was voting, imagine a voting equipment that looks like a TV and has a few buttons for choosing this candidate or the other candidate. So it was shown that it was very easy with a Van Eck style of attack to tell what someone had voted. So just prior to, when that was shown, just prior to the Dutch national elections, the government issued the requirement that any kind of voting equipment should be protected from leaking these compromising information, these compromising emanations, up to 5 meters. This style of attack is often used in order to break the security of things like of cryptographic systems like smart cards, for example. So I'm only mentioning here the simplest of all, just for showing the concept. This is clearly obsolete by now. There are much better styles, but let's use this one as an example. So it's the simple power analysis, SPA. For this one, what the attacker does is that the attacker connects to a device, to an oscilloscope. So let's consider this an oscilloscope on the left, so this device, and it observes, and the oscilloscope or the attacker observes the power consumption. So we connect the device, the smart card, something that does a cryptographic operation, has secret keys there, and performs a cryptographic operation, perhaps for authentication. And then observe the power consumption when the smart card is in operation. So what we see is that every time a specific instruction is performed on the microprocessor of that device, for example, let's say a multiplication or a squaring or some kind of inversion, whenever this happens, there is a pattern that we see on the left on the oscilloscope. So so this device, we don't break it. We don't try to find mathematically how it works. What we do is that we let it run and then see on the oscilloscope the different types of patterns that appear based on the different types of instructions. So these two, for example, these two they seem to be the same. So they would be the same instruction. In this case, it is a squaring, but it's not necessary that we would know that. And there is a different pattern for inversion, different pattern for multiplication. So we know that the cryptographic system is doing a multiplication now because it shows as such when plugged into, when connected to an oscilloscope. In fact, the bottom image has the data encryption standard, which is the DS, as an operation, and it is known that this standard has 16 repetitions, 16 DES rounds of the same group of instructions, and there you can see the 16 of these rounds. So this was about electromagnetic emanations, but there can also be acoustic emanations, so audio, sound. In 1956, in fact, the British were indeed spying on the Egyptian embassy by listening to the sounds produced by its encryption devices. So it was the sound that they knew correlated to an extent to what was pressed, what keystroke there was. So a different keystroke would have a different sound, and this was observed by the British, and they were spying in this way. And a type of attack, a type of experiment that is not terribly difficult to do, and it's common to see in, for example, MSc or undergraduate projects in cybersecurity, is to have a person, to have the situation where a person is typing something and these keystrokes are captured by a microphone, perhaps the smartphone's microphone, perhaps two microphones, that would be easier. And this sound is then offline analyzed. So there is keystroke audio analysis offline, from which one can tell which key was pressed. The more the microphones, the better. In fact, one way to do it is without analyzing the actual signature, let's say, of the audio signal. So this would be a signature into this here. So rather than looking for this signature, let's say that the signature is a B or something. It doesn't really matter, but let's say it's a specific keystroke that is pressed. Well, it doesn't need to be that advanced. It can be, if we use, let's say, 3 or 4 multiple microphones, then we can simply look at the volume of sound. So how high up it goes, and by doing this, we can tell how far each microphone is from the key. So if the microphone that is the closest to the key, for example, is to, let's say, Z, is the one, let's say that is the microphone that is closest to Z, and this is the microphone that has the highest volume recorded, then it must be Z that was pressed, for example. So this is one way to use a very simplistic keystroke audio analysis. And other examples of targeting confidentiality in an emanation security attack, a passive one might be having malware on a smartphone that, rather than capturing the information, for example, from the password while it is, or the PIN while it is typed, instead what it might do is that it might be recording the accelerometers. So it might be an application, perhaps an application for, let's say, runners, so some kind of application that would be expected to ask for privileges in access to accelerometers on the smartphone. And instead of doing that, or in addition to doing that, it is also recording the accelerometer values whenever the user is typing their PIN, is touching their smartphone for their PIN. So in these different types of, or the different ways in which someone is typing the PIN are captured by the accelerometer, because there are these minute movements of the phone every time we are typing something on the phone. And these are captured, and in this way the malware can be recording the PIN, or the password. So rather than, or in addition to its normal function. So this is a passive type of attack, but there can also be an active attack. These are often referred to as teapot attacks. Again, just like Tempest, which is a code name, there is the code name Teapot in this case. And an active attack is an attack which artificially stimulates emanations. So it doesn't passively look for emanations and naturally recording them and then trying to analyze so as to see, for example, what was typed or what was encrypted. Instead, it actively stimulates such emanations. It tries to create such emanations. A very simple way to do that is for a piece of malware, to make the keyboard or any other kind of object on a computer that has an LED to reveal what is being typed based on the LED. So the way that the LED is flashing, the light is blinking. In this way, it might be, for example, creating a code. It might be sending a code to someone who can see the LED. So the person might not be able to see what is being typed on the keyboard, but might be able to see the light as it is blinking. And another one is kind of a bit more extreme, I must say, but it has been published in a paper. It was nicely documented and nicely analyzed, so I'll mention it anyway. It's if there is malware that is on laptops, installed on laptops, has already infected them, and what this malware does is that it creates an acoustic, effectively, network between these laptops, between computers. And this acoustic network is sharing information between them based on speakers and microphones. So rather than sending an email or sending traffic over the network, what the laptops might do, these infected computers might do, is that they might share information, and in this way they lead to data exfiltration based on sound. So through the speakers and through the microphone, effectively an acoustic network.